Hello everyone and welcome to another video. So today I'd like to continue our discussion on vector differential calculus by looking at three ideas, namely the Laplace operator, the divergence of a vector field, and the curl of a vector field. So let's just jump in and talk about each one of these in sequence, starting with the Laplace operator. So the Laplace operator, the way you'll typically see this written is like this. It's del times del, or del squared, or sometimes delta. And all this means is this operator is just take the second partial derivative of the function with respect to x, added to the second partial derivative with respect to y, added to the second partial derivative with respect to z, okay? Now the first thing I think we should probably mention here is, again, let's get the notation straight, right? Does everyone remember this upside down triangle, right? This is basically the nabla symbol, so sometimes you'll hear it referred to as nabla, or it's del, right? Contrast this with the triangle that looks like this, right? This is obviously the Greek word delta, right? It's a capital delta, D-E-L-T-A. Delta, right? Okay, so I just want to make sure we're all okay on the notation, because the other thing that we have talked about previously, right, we said that you had seen a single nabla used for the gradient of a function. So sometimes this is referred to as the gradient or the grad of a function. So this is not that. This is, and it's you can kind of see where it's somewhat related to the gradient of the function, right? The gradient of a function was a bunch of first derivatives, but it actually produced a vector output. This here is a bunch of second derivatives. You add them together to get a scalar output, okay? So again, I just want to make sure we're all okay on the notation. We're actually going to have a video later which actually summarizes all of these different operators together, so hopefully it will all be on one page, but I just want to get that straight first, okay? So what the Laplace operator is this delta operator, or del squared. And again, what this does is it's applied to a scalar function. So if you have a function that outputs a scalar and it's a function of x, y, and z, so it's got, basically you can think of it as 3 inputs, 1 output here, okay? What the Laplace operator on this function does is, again, all you do, like you said, you take the function, you take its derivative with respect to x twice, you take the function's derivative with respect to y twice, function derivative with respect to z twice, you jam and add all 3 of them together, okay? Now again, I want to make a couple of notes here about notation while we're harping on this, right? First of all, this is called the Laplace operator, or sometimes you'll hear it referred to as the Laplacian as well, okay? Do not confuse this vector derivative Laplacian with the Laplacian matrix, which you'll sometimes see in graph theory. This is a completely different operator, has nothing to do with this, okay? That's the first note. So the Laplacian of this function f is a completely separate thing from the Laplacian matrix of a graph, okay? The second thing that I want to note here is also, in terms of notation, unfortunately there's some collision going around in the kind of mathematical and engineering community. Do not confuse this Laplacian or this Laplace operator with a Hessian matrix. Sometimes you'll see this Hessian matrix in the fields of optimization or control theory, and you remember what you see there is sometimes they'll denote it as H, which is I think a much better notation, but sometimes, you remember this H thing? What the H is in optimization and control theory, it's a matrix of second derivatives, of mixed second derivatives, okay? So again, it's almost like it's a second derivative or 2 gradients. So sometimes mathematicians will denote this Hessian matrix as gradient squared f, which again is horrible notation. So I just want to make sure we're all okay here. What we're talking about right now, this del squared, is not this one, okay? So again, you're just going to have to keep that in mind. Pay attention to what field you're doing this and what context you're seeing this Laplace operator, because its definition might change. So again, don't confuse them here. We are not talking about these. We are talking about this thing, okay? So the easiest way I think to maybe look at this is, let's look at an example. And again, I've got more details in the notes. In the interest of keeping this quick, let's move through this somewhat quickly. Check out the notes if you're more interested in the details, but let's just cook up some random example. Let's say I've got two masses floating around in space. Mass A, which has a mass of capital M, and mass B, which has a mass of little m, okay? And as you can probably imagine, you're out here in space, and these two forces, they attract one another through a gravitational constant, right? So the first thing I can do is I can get a position vector from A to B. Let's call this thing R bar, right? And that's really simple how to get that, right? And then I can get the vector of the attractive force from B towards A. And again, check out the notes if you'd like to see the derivation, but you can get this here. And you can see it clearly has something to do with the masses of the two objects and the gravitational constant and something about the distance cubed, right? So again, this all seems to make pretty reasonable sense. Or I guess technically kind of squared if you take this vector into account, right? But anyway, right, let's say you've got this is a vector function, right? You give it a position, x, y, and z. This thing spits out a force vector in the x, y, and z location. This is telling you this vector, actually, I guess we can draw this, right? There's like a vector attracting from, oops, sorry, I guess it's actually the other way around. Did I have it the other direction? Sorry, it's the other direction. It's from B towards A, right? That's this thing P, okay? All right. This thing has nice physical meaning, right? Let's go ahead and define some scalar function. I'm going to cook this thing up, okay? And we're going to see why I cook this thing up in a second. Let's make this thing up, okay? This scalar function, it's just this constant c over the distance between the two, right? So you can clearly see you plug in an x, y, z location. That gives you a distance. I can take the magnitude of that distance, put that in the denominator. I divide with this constant here, so I get a scalar. So 3 inputs go in, 1 single number comes out. That's what this function is, right? And again, you could write this thing down if you like. You can see here's what this function looks like. It's just a bunch of constants, right? You got c, x naught, y naught, z naught, all that kind of stuff. You've got it in there. And now what we can ask is, okay, can I take the Laplace operator of this function, okay? Now, before we do that, maybe what might be interesting, you might be thinking, why the heck did I cook up this function f, right? This function f, does it have any physical meaning at all? Okay, what's interesting about this, as a quick side note, remember our discussion on the gradient of a scalar function? You can take the gradient of this function, which again, this is just single del f. So all this is, right, remember, this is just the partial of f with respect to x in the first entry, then partial of f with respect to y in the second entry, and then partial of f with respect to z in the third entry, right? So if you do this and take the gradient of this weirdo function f, what's interesting is you recover this vector field, which is the attractive force. So we see that actually lowercase f, it's actually a potential function which defines this vector field. Okay, so that's the side note I wanted to say. Okay, that takes us back to our gradient discussion. Now, instead of a single del, let's look at del squared, which is the Laplace operator of this function f, right? That's the topic of discussion. So all I need to do here is apparently take this function here, take its derivative with respect to x twice, that's this term, then take its derivative with respect to y here twice, get our second term, and take the derivative with respect to z twice, that's the z term, add them all together, and what's interesting about this function is that it actually satisfies the Laplacian of f is equal to 0. So that's actually kind of interesting, and again, I don't think I want to do this by hand on the board, so I'm just going to show you a screenshot of me doing this in Mathematica to prove to you that, yes, it works. Each one of those terms are kind of ugly, right? Because you got to take the second derivative of the function with respect to a variable twice. It gets ugly. There's a lot of constants hanging around. But by the time you add them all together, everything cancels out and you just get a big fat 0. So again, there's a Mathematica if you're interested in seeing it for real. That's the Laplace operator. I don't want to spend too much time on this. I just want to introduce the idea of the Laplace operator. We are going to see this show up again when we start talking about things like partial differential equations down the road. So just tuck this in the back of our mind. This is the foundation for some of these PDEs that we're going to be looking at in the future. Okay, so that's the Laplace operator. Why don't you give me a second to erase the board and let's move on to divergence. All right, so to talk about the divergence of a vector field, let's first go ahead and consider a vector field. So remember our definition of a vector field. Let's say you've got some vector field where at any given x, y, z location, right, this vector field is going to define a three-dimensional vector, a component in the x, y, and the z. So again, you can think about this as a vector-valued function where you give it 3 inputs, like 3 positions, and it gives you 3 outputs, like 3 directions, right? So this is what a vector field looks like, right? If you have this vector field definition, we can calculate the divergence of the vector field v, and that's written as this, div v, and all this is you take the component of the vector field in the x direction, and you take its derivative with respect to x. Then you add that to, you only look at the component of the second, right? Second component of the vector field, take its derivative with respect to y, and then lastly, add it to look at the third component of the vector field, take its derivative with respect to z. Okay, that's all it is. So again, all the divergence of the vector field is you can think about is you give it a vector field, this spits out a scalar, which happens to be the sum of these three partial derivatives, right? Again, for notation's sake, one thing that you will also see is I like to write this as div v because it's very clear to me that that's divergence of v. But what you may see this sometimes written down as, alternatively, they'll write this as del dot v. Right? That's the same notation, okay? Now, the reason I want to call this out is, again, pay a lot of attention. This little dot here matters, right? Because you remember earlier, again, we talked about if you had some scalar function f, right? And you wanted to take its gradient, right? That was sometimes written as del f. Like this, with no dot, right? So there's no dot here. So again, keep in mind, you can see how this is kind of a big deal, right? No dot means gradient, dot means divergence. Of course, the thing that maybe saves our bacon here is you can think about this that these two operators are they're inherently different, right? The inputs to this divergence operator, like we said, is you have to give it a vector-valued vector field, right? So you do that, and then you can take the divergence, right? The gradient, you have to give it a scalar function, and then you can take its gradient. So inherently, it would kind of go clang. You couldn't try to do one operation on the wrong type of object, right? And again, we'll summarize this a little bit later, but I do want to just draw that to your attention again. So you've got to be a little bit careful with the notation, okay? But again, divergence just means take some partial derivatives, like first partial derivatives, and add them all together, okay? Now, though, that we said that the divergence and the gradient were a little bit careful about this, let's actually look at if there is a relationship between how these two might play together. So again, let's go ahead and consider some scalar function. So this is some function, maybe it's a potential function, who knows? It's like you give it the xyz location, this function returns a single number, right? Let's say you can take this, it's a twice differentiable function, okay? So if that's the case, we can easily compute the gradient of f, right? This thing down here, by just taking first partial derivatives of the function with respect to x, y, and z, and jamming that into the first, second, and third slots of this vector valued function, right? The gradient here is basically, you can almost think of it like a vector field, right? Because you have a component in the x, a component in the y, and a component in the z, right? Well, if I have a vector field here, why don't I go ahead and take its divergence, right? So all I have to do then is I'm going to go ahead and just first focus on this first element. You can think about this. This is basically the v1 component, right? And what I'm going to do with this v1 component, the first component of the vector field, is I go ahead and to calculate the divergence of this thing, right? It just says, okay, look at the first component, take its derivative with respect to x, right? So here's the first component right here. Take its derivative with respect to x. Then focus on the second component. You can consider this to be v2 in our picture over there. Divergence says, okay, look at the second component, take its derivative with respect to y. So that's here. Second component, derivative with respect to y. And then lastly, you do the same thing for this third element, right? This is v3. So divergence says you look at v3, you take its derivative with respect to z. Here's the third component, take its derivative with respect to z. You stare at this thing long enough and you see, hey, wait a second, this is just the second derivative of f with respect to x. This is just the second derivative of f with respect to y, and this is just the second derivative of f with respect to z. Does this look familiar from about 3 minutes ago, right? This is actually the Laplacian of f, right? So what's fascinating about this is that we end up with the result that for pretty much any twice differentiable scalar function, the divergence of the gradient of the function is equal to the Laplacian of that function, right? And again, maybe for good practice, let's see if we can get some usage with our notation, right? So we said that the way you could write this is the divergence here, and then I got to put the dot in here, right? This is the divergence operator. What is this divergence operator operating on? It's operating on a vector field. The vector field happens to be the gradient of f is equal to del squared f. And now you can kind of start seeing where this del squared kind of terminology or notation comes from, right? And again, just be real careful that this is playing a little bit fast and loose. Like, these two dels are different del operators, right? This del is the gradient operator. This del with the dot is the divergence operator. Together, this turns into the Laplacian operator here, right? Okay, so fascinating, right? Let's look at some properties of this divergence operator, okay? Well, actually, in fact, I'm going to skip this entire thing. If you want to see an example of this divergence operator and how, like, you might be asking, why the heck do I care about this? How does this possibly relate to an engineering problem? Well, in the notes, I've got an example of how this is applied to some compressible fluid flow, and it's going to tell you some interesting information about it, but it's going to take me like 20 minutes to walk through that example here. At the end of the day, all I want to get at is divergence operator. It's just an operator, right? It's just taking a bunch of derivatives and you add them together. That's all it does, right? Some properties of that fall out of this is, it's basically like a linear operator, right? You can think about this if you have two vector fields. That's what f bar and g bar are. And then you have two scalars here. So a and b are scalars. Oops, scalars, right? You can kind of think about this as, okay, sure, you got two vector fields. You can scale those two vector fields by a and b, and then you can add these two vector fields together. That cooks up a brand new vector field. Then you take the divergence of this brand new vector field. Sure, you could definitely do that. Or, since it's kind of a linear operator, right, you could basically do, you could distribute this out. Additivity, homogeneity, all that stuff, and you could write this as this, right? You can take the divergence of the vector fields by themselves, scale the results, and then add them together, right? It's the exact same thing. There's also sort of a quote unquote, it's like a product rule for this, right? So let's consider, how about this phi here to be how about this is a scalar function? Okay, so it's not just a constant number, right? So this is almost like the product rule. When you're taking the divergence of a product of two things, right? You first take the derivative of the first thing, multiply it by by the second thing, add it to the first times derivative of the second, right? It's like a product rule. But now, this is a scalar function, that's phi. Capital F is a vector field. So really, we got to take, when we're saying its derivative, you kind of got to be careful here, right? So the derivative of the scalar function, that's the gradient, right? So here's gradient, that's the derivative of this, times the vector field, plus the scalar function times the derivative or the divergence, you can kind of think of f, right? So that's what you end up with here, okay? And again, just for fun with our notation, okay? Again, you could write it like this if you wanted to, right? So the divergence of something, so its divergence is this part, right? It's the del with the dot. And then over here, you see del with no dot, so this is the gradient portion, right? And then over here, it's scalar function times the divergence. So the divergence is del with the dot again, right? Okay, cool. So that's divergence. Again, let me erase the board and we'll go on to our last one. All right, so our last operator I'd like to talk about is the curl of a vector field. So again, let's consider you've got a three-dimensional vector field. The curl of this vector field, it's then given by this operation. And you can see what this does is it's effectively, you use the cross product mnemonic to kind of compute the curl of this vector field. Again, if you want to refresh on what the cross product was, feel free to check out our other video. We had a dedicated discussion on some vector mechanics, including the cross product and how to calculate it. So I'm going to go through this quickly, assuming you've already seen that or are familiar with it. So again, all you do is you build up your little cross product mnemonic matrix, right? And all that you're doing is you're basically putting partial derivatives in this first row and then the vector field here in the second row. So again, the way to compute this cross product, right, I always like to think of it as, okay, if I'm looking at this I component here, I basically have to look at the determinant of the subblock of everything that is not directly underneath of it. So it's basically looking at this, right? So that's where this term comes from, right? So it's the I component times the determinant of the subblock here. Then you got to make sure you get the minus, right? So then we're going to move our attention over here to the second component, or the j component. So again, I'm focusing here, that's the j here. I look at the determinant of the subblock of everything not underneath of it. That's this here, that's that. And then you do the same thing for k, right? You again just kind of change your attention and focus. And again, this is just nothing more than the cross product. And in fact, when you see that this is just nothing more than really computing a cross product, you can see why the notation you'll sometimes see for curl, it's del crossed with v. Okay, so again, this is kind of a cross product, and I think that is a good way to help you remember what this curl operator is doing. It's really the cross product here. And again, we saw earlier that again, this del operator, it just keeps getting used for this operation of df, basically ddx, ddy, ddz, right? So again, you're just crossing that with the vector. So again, makes pretty good sense from a notation perspective, again. So all you end up with at the end of the day is when you do this, you end up with this, right? So the curl of a vector field, you put in a vector field, right, or a vector function, you get out a vector function with, here's the first component along the x, here's the second component along the y, here's the third component along the z, okay? So that's what it does. Curl, you put a vector field in, you get a vector field out on the other side, okay? Let's look at an example of this, and it might actually help to kind of think, what does curl help measure? So curl is going to help measure sometimes in the field, if you consider this vector field v to be maybe describing like fluid flow, you might think, you know, if there was some fluid flowing past like a ball or something like that. I don't know if I have a ball that I can steal here. Usually I stole my daughter's little fan. Let's say you've got like, you know, a disc or something like this, or a ball, right? And if there's like a vector field, like if there's more fluid flow across the top of this than there is on the bottom, or maybe the fluid across the top is going faster than the one on the bottom, the friction between the fluid and this ball is going to want to make this thing turn or rotate in a certain direction, right? So you can imagine if you're somewhere else in the flow, the fluid around this little ball or this paddle wheel might be different, and it might want to turn in another direction. It might want to turn quicker or slower, etc. We're going to see that's actually what curl is actually helping us measure, is the amount of, you know, quote unquote rotation in a vector field. So for example, let's take a look at this vector field right here. So the x component grows with y, okay? The y component grows with kind of negative x. So it's kind of interesting. In fact, instead of me just talking through, here's a picture of what this vector field looks like if you plot it over just 2 dimensions. You can kind of see here z is not important right now. Okay, so you can see what this is doing is it's sort of this circular motion effectively. Okay, now what we can ask ourselves is, what happens if you place one of these balls or these paddle wheels somewhere in this fluid flow? What's it going to want to do? And you can kind of see by just do a thought experiment. Say you're going to drop in a paddle wheel, which is like this X shape, somewhere into this fluid flow, and you can kind of see that the flow on the that's kind of farther out on the radius is going faster than the flow that's closer into the origin along a radius. So it's actually going to want to spin all of these paddle wheels. You can almost think of it like in a clockwise fashion, right? Can everyone see how that's kind of what's going to go on? So the question now is it going to spin in a clockwise fashion at the same speed anywhere in this flow? Like if you're right near the center of the origin, that it's still going to try to spin clockwise, but is it going to spin as fast clockwise as say you're farther out, right, along a radius? So to do that, let's compute the curl. So the curl, if you compute the curl of this vector field, you come up with a constant number of 0, 0, minus 2. So what that means is actually, right, think about this. Again, we saw that the picture, right, it kind of had a fluid flow like this. You had X, Y, and I think the fluid was kind of, it was going around like this, right? Okay, so now the question is, no matter where you jam one of these paddle wheels in the flow, it's actually got the same tendency to spin in this direction or rotate in this direction. And we should ask ourselves, which direction is this? 0, 0, minus 2. So that's actually into the board, right? So here's the vector 0, 0, minus 2. So actually, according to the right-hand rule, that actually is correct, right? It actually is, oh wait, hold on a sec. Did I just draw this backwards? So, Ha, sorry, I drew the arrowheads backwards, and I'm glad we just did that because this kind of idiot checked ourselves, right? These should all be spinning clockwise. Each one of these paddle wheels should be spinning clockwise, right? And in fact, that is exactly what the right-hand rule is telling us, right? You take your right hand, point it in the direction of the vector, your fingers curl. So yeah, all of these little paddle wheels should be spinning clockwise. And actually, no matter where you go in the flow, they should spin at about the same speed, right? Okay, great. So tell you what, that's an easy example. Let's look at a little bit more complicated vector field. So here's this second vector field that I like to look at. And again, instead of me mangling it like I clearly did here on the board, I can't draw quickly. I'll just, again, flash up a screenshot. Here's what the vector field looks like. And again, you can see as you go farther in the x direction, right, the fluid starts moving faster and faster, okay? And now you can kind of see, again, do the thought experiment. Drop yourself a little paddle wheel somewhere in this fluid flow, and you can see that depending on where you are, you actually kind of might start thinking, wait a second, I actually probably expect both the direction and the magnitude of that paddle wheel rotation to depend on my position, and mostly only depend on my x position, right, in this flow. So again, if you compute the curl, that's exactly what you end up with right here. Right? You end up with this curl of 0, 0, negative 2x. So you can see when x is positive, we get a vector into the board. So when it's positive, we get clockwise rotation, right, of these paddle wheels. And furthermore, the bigger x gets, the more rotational it gets. So if I keep going into the positive x direction, I would expect this thing to be spinning, and the flow is much, much, much more rotational than it is kind of closer to the y-axis. And then similarly, if x is negative, negative 2 times a negative number, you actually get something coming out of the board. So the rotation is actually in the opposite direction. I would expect a counterclockwise rotation of these paddle wheels, which again makes perfectly good sense when you look at the actual geometry of the fluid flow. So I think that's kind of interesting. I think it's a very helpful, intuitive engineering explanation, I think, of what the curl is helping you measure. It's helping us measure the amount of, say, rotation if you imagine this vector field to be describing like a fluid flow. Okay, so that being said, what's interesting now is let's come over here and we can actually see there's a relationship between the curl and potential functions. So let's notice that, what if I compute this thing, the curl of the gradient of a function f, okay? Let's say I've just got some function f. Again, f could be a potential function or just any function. It's just some function of x, y, z, right? You take its gradient, that's really easy. It's just take the derivative of f with respect to x, y, and z and jam it into a vector, right? Now that I have a vector function here, I can take the curl using the cross product notation we just discussed here. And again, I'll save you the nitty gritty. You can see the nitty gritty here in the notes, but if you are just plugging this in, you consider, this first element is V1, this second element is V2, this third element is V3. You're just plugging that into all of these, and you're seeing what you're doing is you're calculating a whole bunch of mixed partials. You're subtracting them, adding them, you're mixing them all up. What's fascinating is at the end of the day, when you do all that, I don't care what your f is, you're going to come out with a big fat 0, 0, 0, right? So what's fascinating is the curl of the gradient of a function is 0. I don't care. And in fact, maybe to make this even more clear, probably what we should have said is I should make this a 0 bar, right? Because this is a vector, right? It's all 0 in all elements, right? So think about the implications of this from the perspective of this rotational flow discussion. Let's say that you have some vector field that is derived from a potential function, meaning this vector function comes from taking the gradient of this potential function, right? That's what you end up with. So if that is true, right, that means that this vector field, it's the gradient of the potential function, right? What we just showed then is that means that the curl of this vector function is 0. If we're interpreting the curl of the vector field as sort of the measure of rotational energy or rotation in this fluid flow, we see that it's 0. So basically, any vector field that is derived from a potential function or any vector field that's the gradient of a potential function is irrotational, right? So kind of fascinating. Okay, so with that being said, I think this is probably a good spot to leave it. I actually want to, we're going to continue this discussion and maybe look at all of these operators in kind of curvilinear coordinates. We've been looking at a lot of these in kind of rectangular Cartesian coordinates, but I do want to take a look at what it might mean if you wanted to take these in, say, like polar or other kind of curvilinear coordinates. And then we should take a quick summary of all of these operators, because we've talked about a lot of things like gradient, Laplace, curl, divergence, all these things, and let's summarize them in their notation and how they're used and all that kind of stuff. I'll put that in a separate video. So like I said, this is a good spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. It really does help if you click on that share or that like or the subscribe. It just helps with the algorithm. And I hope I'll catch you at a future discussion. The new videos come out every Monday, and we can hopefully get together and learn something new together. So until then, I think I'll sign off. Talk to you later. Bye.